Nearly 13,000 feet below the surface, in total darkness, something was appearing out of nowhere. And it handed us a field guide to alien oceans, and then quietly broke the one rule we use to detect life at all. Subscribe if you are into that kind of mysteries, because everything on this channel stays with published science and skips the fluff. Consider the phosphates found in 2023 in ice grains flung from Enceladus, which means phosphorus, the last of life's 6 essential elements not yet confirmed there, is now present in that moon's hidden ocean at concentrations at least 100 times higher than in Earth's seawater. To understand what that means, you have to know why NASA studies the deep sea in the first place. The ocean floor is the closest thing on Earth to the buried oceans of Jupiter's moon Europa and Saturn's moon Enceladus. Crushing pressure, total darkness, and complete isolation from the surface and the sun above it. For most of scientific history, one assumption seemed beyond question. Every living thing, somewhere down the chain, depended on sunlight. Plants capture it, animals eat the plants, and photosynthesis sits at the base of it all. That assumption held until February of 1977. On the 17th of that month, the research submersible Alvin descended about 2.5 kilometers to a volcanic ridge near the Galapagos Islands. The geologists aboard, Jack Corliss and Tjeerd van Andel, expected bare rock. Instead, they found entire communities of animals crowded around warm springs on the seafloor. Nothing there had ever seen the sun. The base of that food chain was not photosynthesis, but chemosynthesis. Bacteria drawing energy from hydrogen sulfide seeping out of the earth. It was the first proof that a complete ecosystem could run on the planet's own chemistry, with no light involved at any step. Those Galapagos vents were driven by volcanic heat, but in the year 2000, a research team exploring an underwater mountain near the mid-Atlantic ridge found something stranger and named it the Lost City. Its pale carbonate towers rise dozens of meters from the seafloor, and they are not powered by volcanism at all. They run on a chemical reaction called serpentinization, seawater soaking into mantle rock and reacting with it. That reaction, described by Deborah Kelly and her colleagues in Nature in 2001 and in Science in 2005, produces hydrogen and methane continuously, with no living thing and no eruption required. The rock and the water make life's raw fuel on their own. Lost City has been doing this quietly for tens of thousands of years, and its cool, alkaline, mineral-rich chemistry has made it the leading Earth analog for the ocean of Enceladus. And this is where the story turns, because Lost City had, in a sense, already been described before anyone laid eyes on it. In 1989, a British scientist named Michael Russell, then at the University of Glasgow, began arguing that life did not begin in a warm, sunlit pool or beside a violent volcanic vent. He proposed that it began in exactly the kind of place no one had yet found, a cool, alkaline hydrothermal vent, where hydrogen-rich fluid rising from serpentinizing rock met the surrounding ocean across thin mineral barriers. In his view, such a vent was not merely a shelter for early life, but a kind of natural reactor, one whose steady flow of chemical energy could help assemble the molecules of life in the first place. For more than a decade, the idea sat at the edge of the field. Russell laid it out in more detail in 1993, but there was a basic problem. No one had ever found a vent that actually worked the way he described. Volcanic black smokers were known and dramatic, and they drew most of the attention. His cool alkaline vents were, as far as the evidence went, hypothetical. The prediction had no example in the real world, and a prediction without an example is easy to set aside. Then came the year 2000, and the Lost City. Here was a vent field powered by serpentinization, cool where the smokers were scalding, alkaline where they were acidic, producing hydrogen and methane from rock and water, and standing well away from any volcano. It corresponded to Russell's predictions, in the words later used to describe it, almost exactly. A model drawn on paper before anyone found the thing it described had been confirmed by the ocean itself. That is the rare case where a theory about our deepest origins was written down first and discovered second. Now carry that earthly discovery across the solar system. In 2015, NASA's Cassini spacecraft flew directly through a plume of gas and ice erupting from the south pole of Enceladus, a moon of Saturn only about 500 kilometers across. Its instruments sampled the spray as it passed. When the analysis was published by Hunter Waite and colleagues in Science in 2017, it showed molecular hydrogen making up somewhere between 0.4 and 1.4% of the gas in that plume. On Earth, that same hydrogen is the signature of hot water reacting with rock, the very fuel that feeds the vents on our own seafloor. Finding it pouring off Enceladus meant the same reactions were almost certainly happening on the floor of that moon's buried ocean. But Enceladus sits far from the sun, where its water should be frozen solid. It stays liquid because Saturn needs it. Locked in a 2-to-1 orbital resonance with the moon Dione, Enceladus is flexed and stretched by gravity on every orbit, and that friction, called tidal heating, melts the ice from within and drives the hydrothermal activity Cassini's hydrogen points to. And then, the same seafloor that confirmed a prediction produced a warning. In 2024, a team led by Andrew Sweetman reported something in sealed chambers resting on the Pacific abyss, about 4 kilometers down in a region called the Clarion-Clipperton Zone. Oxygen inside those chambers should have fallen as microbes consumed it. Instead, it rose. The researchers, writing in Nature Geoscience, called it dark oxygen and suggested that the metal-rich nodules littering that seafloor might act like natural batteries, splitting seawater without a single ray of sunlight or any photosynthesis. That claim is far from settled. The mining company that funded the fieldwork rejected it. Several groups have argued the result is an equipment artifact, and the journal has attached an editor's note while a new expedition heads out to test it again. But the possibility alone is unsettling, and it did not stay confined to the ocean. About 124 light-years away, a claimed detection of dimethyl sulfide, a gas linked to life, in the atmosphere of the planet K2-18b was celebrated as a possible sign of biology. Then several independent teams re-examined the same data and found the signal did not hold up. Only methane was solidly there. A seafloor and a distant world told one story. A single chemical signal is never proof of life. This is why a chamber on the ocean floor reaches all the way out to the search for alien life. If bare geology can manufacture oxygen, then oxygen by itself can no longer be treated as proof that something is alive, and oxygen is exactly what astrobiologists hope to read in the atmospheres of distant worlds. The clean signal we counted on turns out to be forgeable, and yet the same caution cuts the other way. In 2021, Antonin Affolter and his colleagues took Cassini's actual measurements of Enceladus and ran them through a statistical model published in Nature Astronomy. They found that serpentinization of the moon's rocky core, on its own, cannot account for how much methane is escaping in the plume. What fits the numbers best is Earth-like microbes making methane on that seafloor. The authors were careful. This is not a detection of life. It means the possibility of life there cannot be dismissed as unlikely. Step back, and a pattern comes into view. The deeper we look into our own ocean, the more Earth begins to resemble somewhere else, and the abyss becomes our nearest working model of the alien seas we are already flying toward. That is no longer a thought experiment. NASA's Europa Clipper launched in October of 2024 and is on its way to Jupiter, where around 2030 it will begin dozens of close passes over the moon Europa to judge whether the ocean beneath its ice could support life. We are testing our questions on the seafloor and carrying them at the same time to another world. So what NASA found at the bottom of the ocean was a prediction made real, proof that we can now read the recipe for life's beginning in the rocks of a distant moon. Even as that same seafloor warns us, we still cannot be certain when we have truly found someone home. We are only scratching the surface. The next discovery is even more eye-opening. Subscribe before it drops.